Hey there. It won't let me go into slideshow mode without stopping the recording, so we're going to be doing this like this. So today we're going to be looking at curvature, and I'm looking to give you an intuitive derivation of how we get the formula for the curvature of a curve. So what is curvature? We're talking about how curvy a curve is, but what does that mean? Let's look at the curve, right? Let's look at a curve. We want to see how the curvature is changing. So let's find the derivative and visualize the derivative at multiple points, right? We want this to be intuitive. So let's draw the tangent. I guess we can see that over the areas with more curvature, the direction of the tangent vector changes more. So we could call curvature the change in the tangent vector, right? So it's the derivative of the tangent vector, I guess. What are we going to do since derivatives can become negative? Do we have an interpretation for that? I feel like that's something that is directional, right? What is negative curvature? Unless maybe we set a norm, but I'd say curvature is positive. It's a scalar, so if we have any vectors, we want to find their norms. And we're looking for maybe just the change in direction rather than the magnitude. So we could also say it's just the change in the unit tangent vector. But when we're finding derivatives, we usually find a change with respect to another variable, right? We see the change in the unit tangent vector. That's with respect to maybe the distance across the curve. Maybe we call that the arc length. The distance we travel, how much the unit tangent, the direction of the unit tangent, the unit tangent changes with respect to arc length. We do have a problem. We don't usually have curves in terms of arc length, but we can use chain rule to figure that out. Let's look at the math. So we said, let's define t as the unit tangent vector. This is the change in the unit tangent vector with respect to arc length. If we perform a little chain rule maneuver, we can write this as the derivative with respect to another variable, call it t, time, distance, whatever, just for parameterization of the curve, right? And we look at the second term that we just introduced, dt over ds. This is just the inverse of ds over dt, which is the derivative of the function, right? We're trying to see a small change in the arc length with respect to time, right? This is the same thing as a small change in the output. If we're looking just at a small momentary change, because it considers the change in the x, y, and z direction. So let's define this as the velocity, right? Well, we have the inverse of the velocity, so we can rewrite this as 1 over v multiplied by d big T over d little t. The thing is, v is going to be a vector, and d big T over d little t is also going to be a vector. So we can't multiply vectors. I don't think we have that operation. So we're going to have to find the norms of these vectors. I guess we've encapsulated the idea in a formula, right? And now we want to apply it. So let's find a really easy application of this definition of curvature. We just want to make sure it works, right? We want to test it out. Let's take a circle. I'd say it has constant curvature around the radius. If we look at, say, examples of centripetal motion in physics, we can see that at a constant linear velocity, the acceleration is, like in magnitude, always the same, and the direction just changes. This is exactly akin to what we're looking at right now. The curvature is not changing. It's pretty cool. I'd take a look at it if I had some time. So constant curvature all around the radius, but we can say the curvature varies according to the radius, right? A bigger radius means a smaller change in between the tangent vectors, and a smaller radius means a bigger change in between the tangent vectors. There needs to be more change per distance, right? So we can say that the curvature is inversely proportional to the size of the circle. I mean, let's test the theory, right? See if it works. So let's define our curve over here. This is a circle parameterization, right? Now we want to find, let's go for velocity first. So derivative of the output with respect to time over here, that's our velocity. Let's find the normal velocity because we use the normal velocity, right? It's 1 over v and it's the norm of v, right? We see over here, it just simplifies to a, right? So 1 over v becomes 1 over a. Now how do we find the unit tangent? I mean, it's really just the derivative of the output with respect to time, which we defined as v, divided by its magnitude, which we know is a. I mean, we calculated v earlier, and if we just remove the a's, then we have the unit tangent, right? Which is just cos ti minus sine tj. And that's nice. Well, now we need the derivative of this unit tangent with respect to time, and we can say that's negative sine ti minus cos tj. Remember, we find the norm of this, and again, some trigonometric identity shows us that the norm of this is 1. So, I mean, we look at the formula, and we're right. It's exactly inversely proportional to the curvature. So, I mean, we've successfully gone from curves and a definition, used all our ideas of vector calculus and even calculus of a lower year to derive the formula for what curvature is, and we successfully applied it and predicted its behavior on a function. I mean, a simple function, but proof of concept, right? That was pretty sick. I mean, this is how people figure things out. This is how people learn. This is how people discover. I feel like it's a really important thing to always go back, check derivations, you know, actually see it for yourself. Because I mean, it's really different. It's really a different experience, and I had a lot of fun doing this. I really appreciate the project, and thank you. You have a good one.